All right, hello class. My name is Emmanuel Akwa, and I'm here with Joseph Kwans as my group member, and we're speaking on analyzing scheduling algorithms. That's explaining the round robin, first come, first serve, and shortest job first algorithms through simulation and performance. So I'll pass it on to him to talk about the project objectives.
The objective for this project is to implement a simulation program to analyze the performance of round robin, first come first serve, and shortest job first scheduling algorithms. We will analyze the total length of simulation, average turnaround times, average process wait time, average queue length, and max queue length for round robin scheduling algorithm, shortest job first, and first come first serve. We will also interpret the generated results to gain insights into the performance and trade-offs of the different scheduling algorithms. This project aims to provide a comprehensive understanding of process scheduling algorithms through simulation and analysis, enhancing knowledge and practical skills. I will switch over to Visual Studio Code and demonstrate how we used C++ code to generate results for all three scheduling algorithms. So for the code part of the program, we created an enum called scheduling algorithm, which we set the values to be first come first serve, shortest job nest, and round robin. The main components of the process, as we specified, will be the first time the process runs, the arrival time of each process, the CPU time of each process. We'll assign a process ID, and then the first execution time, and then the completion time. The first time the process arrives has a data type of a Boolean because it may be true or false. It may be the first time it's running, or it may not. So that is for the process structure. Again, we have some helper functions. We have a data load file, which is going to help us to load our data file. We have a process scheduler. We have a process completed. We have a compare arrival time and also a compare service time. We'll talk about that in detail as we move along. So for our main method, we created an array list for our time quantum and then our context switch. Remember, these values were provided in the project folder, and then there are 4 sets of data. So we created an array list of 4 to store these sets of data for the time quantum. For the context switch, we also had 6 sets of data, so we created an array list of 6 to store these sets of data. The stats is something that we implemented to help us to be able to work with graphs. So my group partner will be explaining a bit in details of the stats a bit later on. The results file that we are going to generate for all 3 scheduling algorithms will have these column headers: quantum time, dispatcher overhead time, total processes, max queue length, and so on and so forth. So once we run the code, we are going to be presented with these 3 options. Option 1 is first come first serve. Option 2 is shortest job nest. Option 3 is round robin. Any option outside of these 3, the user is going to be receiving an invalid scheduling algorithm message. So the way we implemented the code for each one of these processes is that for the loops, first come first serve and shortest job nest are going to be looping just one time based on the characteristics of those 2 scheduling algorithms. Round robin, on the other hand, is going to be looping 4 times And again, we're going to demo that as we move along. So the loop on this top part is simply showing the time quantum and then the context switch. So we create a variable I to store the time quantum of 4, and then we also created a variable J to store the context switch of 6. Over here, we are going to initialize our Rava queue, which is going to help us to load our data file called input data.text. We're also going to initialize our ready queue, and then we are going to complete the processes. We have a while loop, we have an if loop, well, if condition, and then we have a nested if condition. So for the while loop, the condition here is that if the process are not completed, and then by not completed, we are looking at the ready queue size and then the arrival queue size to determine if the process is completed or not. The first if condition says that if the ready queue is not empty, this block of code must be true. The next if condition is looking at if the process is running for the first time or not. Well, if the process is actually running for the first time. The next if condition looks at the scheduling algorithm, and it has to be equivalent to round robin, and the process ID should not be equal to the last process run. The next if condition is looking at, again, the round robin scheduling algorithm, and is saying that the process service time should be less than or equal to the time quantum. The else here is also looking at the round robin, and this blocker statement has to also be true. The rest of these applies to all three algorithms, because what is going to happen here is that once the CPU time is equal to 0, the code is going to push the process to complete and is going to exit the ready queue. So pretty much what we see down here is how our results files are going to be presented. It is going to be FCFS result.text, SJ n underscore results.text, round robin, which is RR results.text. So that's how our test files are going to be displayed. So without further ado, I'm going to run the code, and then we're going to look at the results files as they come in. So over here, the user is presented with 3 options as we mentioned earlier. So I'm going to start with first come first serve, which is option 1, and I'm going to click enter. So it says simulation results can be found in FCFS underscore results.text. So let's see if we have that results. So that's it up here. We're going to get into the details of it in a little bit, but let's move on to the shortest job nest and see if we're able to generate that results file as well. So again, that file is also generated, and we can see that here, which is at the bottom. Let's see if we can get the round robin results that text to also come up. Option 3. Again, that results file is also here. So this brings the end of my part of the presentation of the code. I'll pass it on to my group partner.
So thank you, Jerome, once again. And skipping the tools and software, my group member talked about that. He also talked about the data structures. So I'm talking about the first come first serve algorithm. So we know that the process arrival time for the first come first serve algorithm schedules processes strictly according to the arrival time in which the processes came in. So with the processes that were provided for the assignment, you notice that they all had their arrival time and their CPU time. So that's where that fits in. And it's non-preemptive. It has a simple implementation because it's in an order. And it's fair because it's one of the first scheduling algorithm because it treats the processes equally depending on when they came into the system. And there's a potential for it to cause starvation that if some processes that arrive late, we are waiting for longer processes to finish. All right. And we have the shortest job first algorithm, and that's the overview that the shortest job algorithm schedules processes according to the CPU total CPU time requirement, giving priority to the shortest CPU. But the process scheduling, the advantage of it is that the shortest job results in shorter average turnaround time and average waiting time compared to the first come, first serve. And a disadvantage of it is that it may cause starvation, where processes with longer CPU burst time may never get executed if all the newer processes have a short processing time. Okay, so I'll be talking about the results that we got from the program that Joseph ran. Okay, so we can see that the total length of the simulation that's over here are the same for the first come, first serve, because they'll all use the same time to compute. And you can tell also to see that the average turnaround time for the shortest job first is slightly lower than the first come, first serve. And the waiting time for the shortest job next, and it's slightly smaller than the first come, first serve. Okay, so we move on to the round robin. Okay, so the round robin has the time quantum. That's the time that a process is allowed to run and have access to the CPU. And the priority based on the queue position. That's depending on when a process comes into the CPU and it's just moving to a ready queue in a cycle form. And it's a cyclic execution. That's when the time quantum expires for a process, the next process takes over, and it does that until all processes have been executed. Okay. So for the analysis of the round robin results, we have when the overhead at the context switch was 0, when the overhead was 0, 5, 10, 15, 20, and 25. And each of the processes had a time quantum of 50, 100, 250, and 500. So these are the results that we got from the program that we ran. And you could see that when the increase in quantum time for the round robin, it reduces the average turnaround time. So for every time quantum, the average turnaround time for the processes with the higher time quantum, that's the red one, see, it's like always lower than the one with the lowest time quantum. And the average wait time for those processes have increased because it needs a longer time for a process will be taking a longer time. And it's the same for the overhead of 20 and 25. Seeing as the time quantum is increasing, it's decreasing the average turnaround time, but increasing the average wait time of the processes. Okay, so that's it for our presentation. And for the conclusion, the project was successfully achieved its objectives by implementing the 3 fundamental process scheduling algorithm: the first come, first serve, the shortest job first, and the round robin. And the hands-on experience gained from designing and integrating the system allowed us to really appreciate what was being taught in class and had added a lot of insight to our knowledge. Thank you.